At this point in class, we've talked about conservation of energy and we've talked about work. So the last little thing that we have to talk about in this unit is power. So power is simply the rate at which work is done. Now remember that work is whenever energy is being added or removed from a system. You can also consider work to be the rate at which energy is transformed. So bare bones definition, power mathematically is defined as work over time. One of our other formulas for work was force times distance times cosine theta. Okay, if you divide that by time, you get something a little clever, where you can look at the d over t. Oh hey, that is velocity. So if you are pushing an object with a certain force and you're making it go at a constant speed, you can just take the product of force and velocity, and that's going to give you power. The units for power, it's a joule per second, which is defined as a watt. Now, the abbreviation for watt is a capital W, which makes it a little confusing because the abbreviation for work is also a capital W, so make sure that you're keeping your units and your variables like clear. That's really power as like a concept. It's how fast work is getting done. So I've got 3 real quick examples to show you. So example number 1, we are talking about classic Jack climbing up a beanstalk. So Jack has a mass of 75 kilograms. He climbs up a beanstalk that is 100 meters. It takes him an hour to do so. We want to know, okay, well, how much power is Jack using? So in this case, we don't really know about Jack's force per se. If he's climbing at a constant speed, then sure, his force is just going to be equal to his weight. But in a lot of problems where you're asked to solve for power, it's easier to approach it from well, what was the change in energy of this system? What was the final energy? What was the starting energy? Take the difference of the two and then divide it by how long it took. So I'm going to use the fact that Jack gained in gravitational potential energy and divide that by the time it took. So 1 hour is 60 minutes times 60 seconds. That's what I've got going on in the denominator there. And Jack's power output is a measly 20 watts. Example number 2, a little practical example for if you get to the point where you're trying to pick, the best electric provider. So this is based on my electric bill. I have a suspicion that I'm getting ripped off. But electricity for me costs 14 cents per kilowatt hour. Kilowatt hour is actually kind of interesting. So a watt, right, is a unit of power, and an hour is a unit of time. So I'm multiplying a power unit by a time unit. This question is essentially asking me how much energy I'm using per month. Okay, thankfully, the electricity company charges you for the amount of energy that you use rather than the rate at which you use it. There's no surge pricing or anything like that. So my neighbor leaves his lights on for a month straight. If you have gotten through dimensional analysis in chemistry, I suspect that this is going to be kind of familiar to you. And so we start out with a 60 watt light bulb. Okay, electricity is costing 14 cents per kilowatt hour. I'm trying to get my units into power times time. So first I got to get the watts into kilowatts because that's what unit my price is in. So there are 1,000 watts in a kilowatt. Writing it like that lets you cancel out the watts. Okay. Then I need to multiply by time, right? Because I'm trying to get to watts or kilowatts times hours. So there's 30 days in a month. There's 24 hours in a day. Okay. I'm able to cancel out days unit-wise. And so right now, what I would have in my little dimensional analysis expression is a kilowatt hour, okay, which is a unit of energy. Then it's just a matter of multiplying that by my price per unit. So 14 cents per kilowatt hour. Triple check in with our units. Our kilowatts go away. Our hours go away. We are left with just dollars. So $6.05. In this last example, I wanted to make sure that I squeezed in a horsepower. 1 horsepower is roughly 750 watts. So we have a horse that's pulling a cart at a constant velocity against a 180 Newton frictional force. Okay, remember, constant velocity, that means zero acceleration, that means the forces are balanced. So the force that the horse applies is also going to be 180 newtons in order for the forces to be balanced. So the horse pulls the cart. She is generating 1 horsepower. We want to know how fast she goes. So we have power, we have force, we're looking for velocity. Okay, this is where we use our last equation, that power is equal to force times velocity, and it's just a matter of a little bit of algebra, solving for velocity. 750 divided by 180 gives us a constant speed of 4.17 meters per second. Okay, so that's really it as far as power goes. It crops up certainly on the AP exam, and it's important that you are able to recognize all the different forms that it comes in, and it's a matter of picking the right equation for the variables that you are given.